All right. Anybody have any questions from last time? We talked about the definition of position and did some position versus time graphs where you start to see how choices of zero position, positive direction, time equals zero affect what the graph looks like. Remember that kind of stuff? Anybody have any questions about homework or anything we talked about? Okay, so today we're actually going to get into the first calculations that I would say you would call physics calculations. And we're dealing with relationships between position, velocity, acceleration, and time. So the last things we have to define before we get into those calculations are velocity and acceleration. So we've already talked about position a good bit. Okay, so first, velocity. And remember, we're still talking about one-dimensional motion. So everything we're talking about is motion along a line. And an object can only go one way or the other way along the line. Well, velocity is a measure of, so it measures how quickly the position is changing. And the velocity v, to relate it to the thing that you're more used to thinking about, is plus or minus the speed and the sign is the direction that the object is moving at that instant. So the sign is the direction, the object is moving at that instant. Okay, so speed, you know, I mean, from your speedometer, from using cars, speed doesn't have a sign. It's always positive. If you drive to northern Minnesota and then drive back, it says you're going 65 miles an hour on your way heading north. And then on your way back, it still says positive 65 miles an hour. There's no sign, okay? If your speedometer actually measured the velocity, then one of those two ways, it would say you're going positive 65 miles per hour. And when you go back the other direction, it would say you're going negative 65 miles per hour. So the velocity takes the speed and just adds on the sign to it that tells you the direction, okay? So for example, if you had a car that's going this way at 30 meters per second, and you decided that you were going to call your positive direction this way, that then means that the negative direction is the opposite. The velocity would be plus or minus 30 meters per second. And then you would look at the direction the car is going. It's moving in the negative direction. And so it would be negative 30. Okay? On a position versus time graph, and remember this is one-dimensional motion. We're only going to use position versus time graphs for one-dimensional motion. So when we get to 2D, you won't see these anymore. But a position versus time graph, the velocity is the slope of the tangent line. And remember that with slopes, that's a positive slope. That's a zero slope. And that's a negative slope. Okay, so for example, let's think about a position versus time graph of a motion. So let's say an object's moving like that. And let's think about the direction the object is moving in at three different instants. Okay, so I'll call this instant A, B, and C. Okay. So at instant A, like we did in lab this week, we'll draw a tangent line by drawing two nearby points and then sketching the line that goes through it. What's the sign of that slope? Positive, yep. And so what direction is the object moving at this instant? Positive, negative, or stopped? It's moving in the positive direction, yep. At B, I'll draw the two nearby points, draw the line that goes through the points. What's the slope of that line? Zero. And so what direction is the object moving, I guess? What's the object doing?
Stop.
It's stopped, right? The object is at rest. And then at the instant C, draw the two nearby points, the line through them. What's the sign of the slope of that? Negative. And so in this case, at this instant, the object is moving in the negative direction. Okay, let me do an example problem where we connect mathematically what the graph tells us to physically what's happening based on our choices of positive and negative. So let's say that our position versus time graph looks like that. And this is the instant that we're interested in. And the object is moving along this line. And we have decided that our positive direction is this way, which means our negative direction is this way. At the point on the position versus time graph that's shown, which way is the object moving? Okay, so take a second and see if you can think through this. You're going to start by figuring out the sign of the slope of the tangent line, and then you're going to use that to figure out, is the object moving to the left or the right in the physical world, you know, in the real world. This is the real world. This ain't no mathematical world, the real world. So I'll give you just a couple seconds to think about that. All right, so to draw the tangent line, draw the two nearby points, draw the line through it. The tangent line has a positive slope. So the velocity is positive. So the object is moving in the positive direction. And because we decided that positive is to the left, the object is moving this way. All right? Units for velocity are always units of length divided by time. We're almost always going to use SI units. And so in SI units, velocity has units of meters per second. Okay, so next we have to talk about acceleration. Velocity, I said, measured how quickly the position is changing. Acceleration measures how quickly the velocity is changing. So measures how quickly the velocity is changing. In 1D, non-zero acceleration can only mean that the speed is changing. Okay, that's because there's no such thing as really changing directions in 1D. There's only going this way or that way. So all you can do is slow down until you stop, and then you start going the other direction. So in 1D, acceleration means a speed change. In everyday speech, we use the word acceleration, tend to use that to mean speeding up, and deceleration to mean slowing down. We're not going to use that here. Acceleration is only going to be defined by its sign, and everything is an acceleration, whether it's speeding up or slowing down. Okay? When we get to 2D in a couple weeks, acceleration can mean speed change. And or it can also mean turning. So you can have a big acceleration in 2D even if the speed is constant. And you know the feeling of like being in a car trying to hold a constant speed as you go around a turn, and you're pulling to the side. That's an acceleration that you're feeling even though the speed of the car is staying constant. Okay, but in 1D, there's no such thing as going around a turn. There's only changing speed. Okay, what do the signs of the accelerations mean? If I made you guess, probably most people would guess that a positive acceleration means that the thing is speeding up, and a negative acceleration means that the thing is slowing down. And that would make sense and that would be nice, but that's just not how it works. So it's a little more complicated than that. Okay. So the sign of the acceleration, here's what it means. If the velocity and acceleration have the same sign, it means the object is speeding up. If the velocity and acceleration have opposite signs, it means the object is slowing down. The only other possibility if you have acceleration is that the velocity is equal to 0. Well, it can't be slowing down if the velocity is 0 because it's stopped. So this means that the object is speeding up in the direction of the acceleration sign. Okay? So the object is speeding up in the direction of the acceleration. Okay, how can you tell acceleration on a position versus time graph? So on a position versus time graph, and again, this is for one-dimensional motion. Acceleration is shown by the curvature. So if the graph is part of a concave up curve, think of this as like a face. This guy has a positive mental outlook. So this is a positive acceleration. Concave up. So this is a positive acceleration. If it's any kind of line, and it doesn't matter what slope you're talking about, that's a 0 acceleration. And if the curvature is part of a concave down shape like that, that's a negative mental outlook, so that's a negative acceleration. Anybody have any questions about that? Anything on acceleration? So let's do another example. Let's say this is our position versus time graph. And let's say this is the point that we care about. And we want to figure out what's happening in the real world. Considering that we have chosen our positive to be going again to the left and our negative to be going to the right. So at the chosen point, Which way is the object moving? And is it speeding up or slowing down? Okay, well, to figure out which way it's moving, we need to figure out the sign of the tangent slope. So I'm going to draw the two nearby points, draw the tangent line. It looks like that. That slope is negative, and so the velocity is negative. Okay? So the object is moving in the negative direction, which on the picture of the real world is to the right. With me on that? Now what about the acceleration? At that point on the graph, is that part of a concave up, a smile, or a frown, you know? Or is it a line? At this instant, well, the red line is just something I've drawn. That's not the position versus time graph. What matters is the black, the actual curve of the motion. So it's part of a concave up graph. So the acceleration is positive because it's concave up. And now we look at the sign of the velocity and the sign of the acceleration. They're opposite. And so since these are opposite, this object is slowing down. So what we've figured out is that in the real world, the object at this instant is moving to the right and slowing down. Units for acceleration are units of length divided by units of time squared. So that could be, you know, miles per hour squared or millimeters per year squared or whatever. If you're in SI units, that means meters per second squared. Okay, so that's velocity and acceleration. And now we're ready to get to some equations that relate velocity, acceleration, position, and time. Okay. So now we're moving on to constant acceleration equations in one dimension. Okay, there's no reason that a motion has to have constant acceleration. You know, constant just means it never changes. So like look at the black curve that I drew here. You can see that we have a negative acceleration for the first half of it and then a positive acceleration for the second half. So obviously that's not constant acceleration. There's nothing that makes that motion illegal or anything, you know. But we're going to study constant acceleration motions because it simplifies the calculation a little bit, and there are some important motions that do have constant acceleration, okay? So not all motions have constant acceleration. But some important ones do, and so that's what we're going to do calculations with. A lot of motions where things are under the influence of gravity have constant accelerations. We'll see a ton of examples of things that do. Any object, any projectile motion where you don't have a ton of air resistance, or any free fall problem where a thing is dropped, those all have constant acceleration. So those are some types of problems that we'll do, okay? But remember that the equations I'm giving you here only work for constant acceleration, all right? Okay, so I have to define some variables first. So let P sub I and V sub I be the position and the velocity at the instant when time is equal to 0. And let P sub F and V sub F be the position and velocity at time t final. And when you think about these two instants, by the way, think about time equals 0 being when you turn a stopwatch on, you click the button on, and it starts counting. And TF is when you turn the stopwatch on to look at the, turn it off to look at the time, you know? Like if you're timing a race or something. T equals 0 is when you click it on and the time starts counting. The person crosses the line and you click it off, and that's T final, okay? And whatever number the stopwatch says, that's T final. Okay, well then given these definitions, here are the three constant acceleration equations. The first one says V final is equal to V initial plus the acceleration times time final. The second one says P final is equal to P initial plus V initial times time final plus 1/2 times the acceleration times time final squared. And then the last one says 2 times the acceleration times the quantity P final minus P initial is equal to V final squared minus V initial squared. So that's it in 1D. Those are the three constant acceleration equations. And so with these, if you know enough about the acceleration and how far the thing is gone when you click off the stopwatch and all these different things, you can calculate other variables that you haven't measured. Okay, and you can figure out stuff about the motion that way. So I'm going to first, I know a lot of this seems really abstract. We haven't done an example problem in a while, but I'm going to sort of abstractly give you a set of steps you can follow for using these equations. And then we're going to do some examples, and I'll go through the steps really carefully with the examples, okay? So just bear with me while we go through the steps, and then we'll show how to use it, show it in practice. Okay, so here are the steps for using the constant acceleration equations in 1D. The first thing you have to do is choose a position equals 0, a positive direction, the instant that you turn the stopwatch on, time equals 0, and the instant that you turn it off, time final. Okay, so the first step is choose a location that you're going to call position equals 0. That's the reference point in your real world. A positive direction. An instant that you're going to call time equals 0. And an instant that you're going to call time final. So time equals 0 is stopwatch on. Time final is stopwatch off. Choosing the location, your reference location in your positive direction, these are up to you. There's no right or wrong for this. There's sometimes ones that'll make the math a little simpler, but no matter what you choose for these, you can solve the problem. You just have to be consistent through the whole problem once you make those choices. The two instants, though, those probably, in most cases, there's a right and a wrong. And if you choose wrong, then you won't be able to solve the problem. So the way you choose these is instance. You have to choose instance when you know information. And when you're trying to calculate information. So when you want information. Okay. So like, for example, if a problem statement says something about the object starts at rest and then later it's at this position, well, you have information when the thing starts moving. You know that it's at rest, and you have information about where it is later on, and so those are going to be the two instants you choose. Okay. Next, if you look through all of these equations and listed out all the variable names that pop up, there's a total of 6. And I'm going to list them right here. So out of these 6 variables, time final, acceleration, P initial, P final, V initial, and V final, list which ones you know, and which one you want, you're trying to calculate. Third, and most of the time this is the last step, look for a constant acceleration equation of the 3 that I gave you that has the variable you want because you can't use an equation to solve for a variable it doesn't have, you know. And every other variable in the equation is known. Because you can only solve for one unknown in in a single equation. So if you have two things you don't know, then you can't do anything with it. Sometimes this isn't enough. Most of the time it will be, but so this step 4 I'm putting in parentheses because you won't always need it. But if no equation works, try solving for TF or acceleration. You know, find an equation that'll let you solve for TF or acceleration. And then go back to step 2. Now that you've figured out more information, now you can go back and maybe there will be an equation that works. And that's it. That's the whole process. I'm guessing no one has any, I mean, you haven't seen this, how it works yet, so probably no question, but anybody have anything that pops into their head? Okay, well, let's do some examples. So now we're going to spend a good bit of time just doing examples. So let's say that a car is traveling 40 meters per second and it hits the brakes. It stops 30 meters later. So first, let's calculate the car's acceleration. And second, let's calculate how long and like how much time it takes for the car to stop. Okay? There's no way you could stop in 30 meters, I don't think, if you're going 40 meters per second. That's like 90 miles an hour. Stop in 30 meters. How far is like 3 of these rooms? Anyways, that's the numbers we're going to use. Okay, so we're going to just go step by step through this process. So the first thing we have to choose is a position equals 0 and a positive direction in the world of the car, you know. And then we have to choose an instant when we turn the stopwatch on and an instant where we turn it off. Okay, so if the car is going this way, then at this instant it's going 40 meters per second. And here it's at rest, it's stopped. And the distance between these two is 30 meters. Let's choose our 0 position at the location where it's going 40 meters per second, so I'll call that 0. And our positive in the direction it's moving, which means negative would be the other way. So we've chosen our 0 and our positive direction. Now we have to choose the 2 instants. And remember, these choices, we could have done anything. And we'll do this problem again after we're done with different choices of these. And you'll see what changes and what stays the same. But now the crucial ones are making the right decisions about time equals 0 and time final. Okay, so what are the instants where we have information? Yep, At the instant that you hit the brakes, we know the speed and the direction, so we know the velocity, okay? And when it stops, we know the velocity is 0 because it's at rest, and we know that it's traveled 30 meters. So those are the two instants where we know stuff. Is there an instant where we're trying to find stuff? Well, no, because remember, acceleration, this is constant acceleration, so the acceleration that we're trying to find is true over every instant. You know, it stays the same, okay? So we're going to choose time equals 0 to be the instant the car hits the brakes. And time final is going to be the instant that it comes to rest. Okay? And now we're going to, so I'm going to list out these 6 variables so we don't miss any as we go. And I'm just going to go down this list and figure out which one we're looking for and which ones we know. Okay, do we know time final? That is, do we know when we turn off the stopwatch what it says? No, it doesn't give us any information about time. But for now, all we're trying to figure out is the acceleration, so I'm not putting that in. We'll worry about part B when we get to it. Do we know the acceleration? No, that's the thing we're trying to find. Do we know the position at time equals 0? Okay, so time equals 0 is when the car is right here. Do we know its position? We do, it's 0. That's where we chose our 0. So Pi is equal to 0. Do we know the position at time final? We do. If you start at 0 and go 30 meters in the positive direction, you're at position positive 30. I'm going to, at least at the start, be really careful about the signs because that's something you always have to think about. Do we know? Yeah. Do we know the velocity at time equals 0? Yep, the speed is 40 meters per second, and then you have to think about which direction it's going in. Is it going in positive or negative direction?
Positive.
Positive, that's right. So V initial is positive 40 meters per second. And then do we know the velocity at time final? Yep, it's at rest, so that's 0. And now we're done with all this. So now we can look for an equation and see if there's one that solved this. Since we're looking for A, and 2 of these equations also have TF in them, we know that those 2 aren't going to work. So the only one that could possibly work is this third one that doesn't have TF in it. So let's see if that one will work. So I'm going to write that down and let's look at it. So that equation says 2A times the quantity PF minus PI is equal to VF squared minus VI squared. It has A in it, so that's a good start. And now let's go through the other variables in it and make sure we know them all. PF, we know it. PI, yes. VF, yes. VI, yes. So this equation is going to work and let us solve for acceleration. Okay? Any questions about that? I know I went through that kind of fast, but... Okay, so you don't have to do this. You don't have to carry the units through everything, but at least for the first time or two, I'm going to do these calculations, including units, so you can see that if you keep the units in and do the calculations carefully, the units will all come out for the answer that, it'll all work out the way it should for the answer you're getting. Okay, so let's put in the variables that we know. So, hold on. Sometimes this just loses sight of the pen. Okay, so 2A times the quantity. P final was 30 meters. P initial was 0. V final was 0. V initial was 40 meters per second. Um, 30 meters minus 0 is just 30 meters. So I'm going to multiply all these together, and we get, you get 60 meters times A. I rearranged some stuff just so you can see sort of, we're trying to isolate A, solve for A. And then on the other side, you have 0 minus 40 squared times meters squared per second squared, because you have to square everything in those parentheses. So this is minus 1,600 meters squared per second squared. You can divide meters from both sides. Then this goes away, and one of these 2 meters goes away. And then divide both sides by 60, and you get that A is equal to negative, question? Negative 26.7 meters per second squared. So the units worked out. Those are the units, the SI units for acceleration. And our answer is this, a really big magnitude of acceleration. Does it make physical sense that we got a negative acceleration now? Well, what's the sign of the velocity through this whole motion until it stops? Positive. And so, and is this car speeding up or slowing down? Slowing down. So remember, slowing down means velocity and acceleration have opposite signs. So we expect acceleration to be negative, and that's what we got. Okay, and thinking about it that way at the end of your problem, thinking about whether you can make sense out of the signs is a pretty helpful way to find mistakes you might have made. Like, say, for example, if I'd forgotten the negative sign here when I squared this 40 meters per second, I would have gotten acceleration as positive. Then I would have thought through those steps and thought, wait a second, that's saying that this car is speeding up. I know that's not true. So you can find a lot of mistakes that way. Okay, so now part B. Now we're trying to find time final. We're trying to figure out what the stopwatch says when the car comes to rest. So the first question is there any reason to change our choices of position equals 0, positive direction, time equals 0, or time final? There's not. We still, that the time final we're trying to figure out is happening at one of our choices of the times. So that still works perfectly well. And the position and direction choices are arbitrary, so we can keep those too. So those same choices still work for this one. So we can just skip right to the second step where we go through the list of variables, figure out what we know and what we want. TF, this time that's what we're trying to solve for. Acceleration, well, we just figured that out in part A, so now we can use that. So acceleration is negative 26.7 meters per second squared. All the other stuff, this is true anytime you keep the same choices. All of the values stay the same. So anything we knew before, we know now. So P initial is 0. P final is positive 30. V initial is positive 40. And V final is 0. All right, is there an equation that works, that has time final in it and everything else in it is known? There's actually two equations that work here. This one works. V final is equal to V initial plus ATF. And this one works. P final is equal to P initial plus V initial time final plus 1/2 A time final squared. Whenever that happens and you have multiple choices, take the simpler one. This one is always the simplest one, so we're going to use that one. Even though we could use this one, we'd have to do some squares and stuff. So let's just skip it. So I'll plug this stuff in. 0 is equal to, so this time, I think you'll take my word for it that the units would work out if we kept them all and did it carefully. I'm just going to use the numbers. Just remember to put your units on your final answers, okay? So V initial is 40. Acceleration is 26.7 times TF. Add 26.7 TF to both sides. That's equal to 40. And then can someone divide 40 by 26.7 for me? So TF is equal to 1.5 seconds. Any questions about that? All right. Well, I know you haven't seen a lot of this yet, but I want to do this same problem again with just a different choice of a 0 position and a positive direction, and give you some time to try to work through it, think through it, and then I'll go through it and you can see if there are places where you're getting confused, okay? So this time, we're going to calculate, we'll just do it for acceleration. Calculate the acceleration in the problem above. But this time, bless you. we'll use, so here's the car when it's going 40 meters per second. Here it is when it's at rest. These are still 30 meters apart. But this time we're going to put our 0 position at the point where it stops, and our positive direction going this way. So that means negative is this way. You're still going to have to use the same instance, time equals 0 and time final. But take a few minutes and see if you can work through these steps now that we've made these changes to the 0 position and the positive direction, okay? And feel free to compare answers to each other, talk to me. But I'm just going to give you a few minutes until everyone looks angry, and then I'm going to go through it. Okay. So now we're going to list what we know and what we want. We don't know time final, and we're not trying to solve for it. We're looking for the acceleration. P initial. So in the first example, that was where we put our 0. It's not anymore. So now what's the position at time equals 0? Yeah, exactly. If you start at 0 and go 30 meters in the positive direction, your PI now is positive 30. What's the position at time final?
0.
0, perfect. What's the velocity at time equals 0?
40.
The speed is 40. And then remember that we switched the directions. It's moving in what we're calling now the negative direction. So this is negative 40 meters per second. Are you with me on that? And then what's V final? It's at rest, so yep, so it's 0. Now it's the same equation as before that works to solve for this. So we're going to use 2a times the quantity pf minus pi is equal to vf squared minus vi squared. So we have 2a times 0 minus 30 is equal to 0 squared minus negative 40 squared. So that says negative 60a is equal to negative 1600. And so A is equal to positive 26.7 meters per second squared. Okay, let's think again about the meaning of that sign, okay? Last time we got a negative answer, this time we got a positive. Is the car's velocity in the positive or negative direction in this setup?
Negative.
Negative. Is it speeding up or slowing down? It's still slowing down, it's hitting the brakes, right? And so if it's moving in the negative direction and slowing down, what do we expect the acceleration sign to be? Positive, and that's what we got. So even though the number we got looked different, and some of the other numbers look different too, the story that it tells is the same. We know it's moving to the right and slowing down, and this is the amount that it's slowing down. Okay? Let's do one more. So let's think about a ball rolling up a ramp. So here's the point A and the point B. And these 2 points are 1 meter apart. And when the ball, so it's rolling up the ramp. When it goes past the point A, it's moving at 3 meters per second. And it takes 1 second to reach the point B. Let's calculate the acceleration. And then second, let's calculate the elapsed time to get from A to B. Well, I shouldn't write it like that yet. We haven't made our choices yet, but what's the, how long does it take to get to B? That's a better way to say it. How long does it take to reach the point B? Oh, wait. I already gave you that. That's not what I want to calculate. Let's calculate. Okay, this is for real now. What's the velocity when it reaches B? Bless you. Okay, so let's choose the 0 at A and the positive direction up the ramp. So negative would be down the ramp. And what about the times? What's going to be the time equals 0? It's like the first instant in the problem where we're given information or trying to calculate information. So that would be when it passes the point A. And then what would be our time final? Yep, yep. Okay, do we know what the stopwatch says when it reaches B? Yeah. So time final is 1 second. We're trying to find the acceleration. Do we know the position when it passes the point A? Yep, that's 0. Do we know the position when it passes B? Positive 1 meter, yep. Do we know the velocity at time equals 0? 3 meters per second, and it's moving in the positive direction, so it's positive. Do we know the final velocity? We don't. We're trying to calculate that in part B. So this is it. Okay, so what can we use here? The one that's going to work is this one. PF is equal to PI plus VITF plus 1/2 ATF squared. And just to see that this is going to work, it has A in it, so that's a good start. And then PF, yes. PI, yes. VI, yes. TF, yes. So everything in the equation is known besides the thing we're trying to solve. Okay, so 1 is equal to 0 plus 3 times 1 plus 1/2 times A times 1 squared. So 1 is equal to 3 plus 1/2 A. Subtract 3 from both sides and you get -2 is equal to 1/2 A. Multiply both sides by 2 and you get that the acceleration is -4 meters per second squared. It's slowing down, so acceleration and velocity need to have opposite signs, and they do. Okay. And now we want to calculate the final velocity. Is there any reason to choose different instants, time equals 0 and time final, to calculate the velocity at point B? No, those will still work. The thing that we're trying to calculate still happens at one of our choices, so this will be perfect. Okay, so time final, these are all going to be the same, plus we know the thing we just calculated. So time final is 1 second. Acceleration is -4 meters per second squared. Initial position is 0. Final position is, how far was that? 1 meter. Initial velocity is 3 meters per second, and we're trying to find the final velocity. And it's always good news when the simplest equation works, and it does in this case. V final is equal to V initial plus ATF. You can see this equation has V final, and then VI we know, A we know, TF we know, so it's going to work. So V final is equal to 3 minus 4. Oh, son of a. That's what I get for trying to change this problem on the fly. It never happens. It makes time go backwards. Okay, stupid. So, well, do you see what the problem is? Time final is 1 second. And so this comes out to be -1 meter per second. -4. Okay, 1. Okay, just 1 second. Let me think about this for a second. Anybody see anything I did wrong here? I think maybe this just doesn't work the way I have it set up. P final.
Velocity faster.
Yeah, right. I think that's what I would have had to do. Yeah. Okay, so 3 1/2 a times time squared. Get that acceleration. Okay, well, so the way I set it up just doesn't work. So sorry about that, but anyways, that's the procedure, blah, blah, blah. Okay, we'll do some more examples next time that will work.